correctly. All right, welcome everyone to the new module. We're going to be looking at Circuitworks a little bit today. There's a lot of things that this can help to do. One of the most helpful of which is give us a visual representation of scale of parts. They do have a built-in library. We're going to kind of walk through some of the details here because this is where you'll need to know some bits of information, maybe not all of it, but some bits of information. What you're going to need to do first is you're going to go to the add-ins. So simulation, we don't need added in. What we do need is over here, Circuitworks. So we have to click this. A couple of you will have this tab show up. You'll go to open the ECAD file, and then it'll prompt with another install feature if you haven't looked at this already. So go ahead and let it do that. I think will ultimately have to close out of SolidWorks and restart. So once you're done with that, then you're going to come to, where in this case, your C drive, or in the case of Mac, I think it's just under users and public. So it's still under your equivalent to the C drive, but it shows up under the Finder different places. Public documents, SolidWorks. So same place you've found other tutorials and other components. In this case, we're looking for Circuitworks. And the example that we're running from is this IDF3 format. And we're looking for this one. So this will bring up a window. A quick note here, depending on what screen resolutions you're running at, you will run into some potentially weird scaling issues. If that happens and you can't see the entire menu, the letters are very large over here for the display scaling. You'll need to go back and change your screen resolution to 1920 by 1080. This is just a thing that, because of certain aspects of this program, it's not going to scale properly outside of that resolution. You're going to see a lot of issues relating to the scope and scale of this. So you want to focus on these being, and that car alarm is distracting. That's frustrating. We might need to just, in case, but I don't know if it's next door or not. I can't tell. It's close by is the problem. We have, maybe it's not ours. It's frustrating. We have a number of different components. They have a component library. We'll get into that. Don't worry, I'll fix that little blip in post. It'll be great. So there's a number of different parts that they build for this circuit layout. This is helpful for trying to lay out housings, figure out tolerances, clearances, etc. They don't have all possible electronic components in this, but we'll look at some specific examples here. So we're looking for this cellphone.enm. In the assignments, you'll notice that you're supposed to have all of these other files and Eagle files and things for the board, for the four-wheel drive control board. We don't actually have those files on hand, so I had to start recreating some of them during Tuesday's class. So that's why you'll see a bunch of the drawings and schematics, as well as the data sheets that are attached to this week's announcement. So those of you that never look at announcements need to start, because that's where we have to put important information. These components have a bunch of different properties which we can update and change as needed. This is possible for this. Okay. So what we're going to find is these properties. Here in our secondary window. They're specifically having us look at this set. What we can't see from this side is the components that are laid out on the opposite side of the board. So when we go to render it, you're going to find out a few new and different things. So another area where the display scaling gets to be really bad is in these side windows. So this is a representation of the component, and we're going to mess with the component height. So this is going to be 2. This one, oh no, they're doing so this I'm going to leave as 0.05. This is one of the other ones that we look at here shortly. I think we changed that one. But they're looking at the buzzer. There it is. So the component properties of the buzzer. This is 2 millimeter component height. It's a class B device, or a type B. They use a couple different abbreviations for classes. A lot of these part numbers you can't find a direct cross-reference for. So I went through some examples in class on Tuesday, but I'll go through some here as well. So a company like Newark, for instance, when we're looking at these component names and IDs and things, a few of them are things that you can identify. So 0402C is indicative of a size and type of device. So that's a capacitor 0402. So 0402 capacitor looks like this, an extruded square or something of that type. So there are different types, different specs, all of that goes into the particular part numbers. These part numbers are obviously nothing close to what we have listed. But we can get some sort of a sense of what some of those components are and what they should look like. So you can cross-reference sort of some of them, if not all of them. So there's a bunch of different geometries here that we're working with, but you can see that they're all, for the most part, represented as simple shape extrusions in order to minimize the amount of memory required. So there's a lot in here and a lot in their component list. There are a couple filters and some other things. There's also some more complicated components, such as these guys. So I can't rotate their view because that's not a live window. It's just a representation. We'll take a look when we go to actually build this. We'll take a look at what some of the process is here. So these two, as you're selecting components, it'll highlight them in red as long as you can see them. Let's see. Yeah, so long as you can see them, it'll highlight them in red. Some of them are on the other side of the board. So there's also what's called a keep out region, where you have to keep things clear because of mechanics for an external housing or something that needs to remain clear. So there's a lot of different things that we can represent on these. But here we're working on the buzzer and updating some of the information. So now we've got that information and we'll save it in the part. So once you're done, just like always, hit the check mark. Then you can apply filters to things that are on the screen to be able to see. For instance, plated holes. The example they give is depending on where you have this slider, some of them will be illuminated and then others will be illuminated. So the idea being that all of those holes are above this minimum size threshold. So this goes the other way and only shows something larger than, and then it's a decreasing scale for that one. So there are a lot of things that we can use this to tell us about in terms of the finished layout. So it's helpful to see how some of these tools work. The building of individual components. So this is one of them. If we take a look and have it build the model, so here's the model. This is made using things that we already understand. So it's a simple sketch with a simple operation. So a simple feature applied. All very small stuff, 0.5 millimeter thick. So not genuinely big things. They did add a 3D sketch so that they could put a coordinate system in it. I think so that they can get a clean mounting point for origination when they go to do assemblies. So we don't need to make any changes to this. They're just trying to make you aware of where the tools are and what they're made from, how these different components come together as assemblies from lots and lots and lots of parts. One other thing, there should be under the design library a components category. So there should be a component library that shows up here. For whatever reason, that's not the case. So you can come up here and click component library. This has a lot in it, but it also doesn't. So there are a lot of devices that aren't represented. And each of these can be built custom and have properties added. So some of them you're not necessarily going to see in the same manner. But we can take a look at what these do, how they're actually done, because there's a couple techniques in there that I had not seen a practical use for until maybe this one case of making electronics. So this one, not so interesting. It's a rectangular box. This other one, we want to build out in order to see how they are done. So it's stuff that we should already be familiar with. I noticed that you have to change views a couple times sometimes to get here. That is not it at all. No, don't save. That is most definitely not it. Let's try that again. No. That's very interesting. Why? Why is that not showing up in full detail? So that's very interesting. Let's go back to the component library because that isn't right. 144. Interesting. Okay. So we'll take a look at this one because there's supposed to be another variation of this, but I guess that one's just a far more simple representation. So this is one of the few areas where we'll see this technique used. So starts off, you roll back the feature set as an extruded rectangle. Then we have a thin extrude. So this is a sketch and a thin feature. So apparently this is one of the few instances where the thin feature makes sense, is you sketch a path, constrain it within that path, and then you set values such as the auto fillet. So the auto fillet helps to get you the curvature that you need. Then you do a simple array pattern, and then you mirror it. Then you rinse and repeat again. Then you do the nice chamfer at the top. And the lettering. So this gives us an idea how these are actually constructed. Some of these components, some are a little fancier than others. That's okay. It's really helpful to have names on the tops of devices that are made for Circuitworks so that you can tell either what it is or what it was supposed to be. All right. So once we know we've got the components in place, then you come up here to do a build model. Now, just for entertainment, I'm going to see if this is more representative of what you're going to see. So I'm looking at utilization. When I go to have this start building, because this is going to make your laptops grumpy. Some of you will overload them. So it's not going to create the assembly if you've got other open parts, even if that's a blank part. Because the dialog box is open, you can't do anything, you're held hostage. So you have to close out all the parts, not the program as a whole. But you do have to close out all the parts. All right. So if you have something selected and you hit build model instead of the overall total of the part, it's going to be incomplete. So we're going to overwrite. So it's got to go in and create the parts. And it'll actually kick up use across almost all of the cores. The very first render took a very long time by comparison. So to have an assembly done this quickly is pretty impressive. So now we have the physical representation, bunch of stuff on the back, bunch of stuff on the front. So this is all components from their library. You can build custom components, and that's one of the things that we're going to get into today. So there are some difficulties and challenges in those regards, but it gives us a pretty good spatial representation of what things are like. So usually about this stage in the design, people get to be excited because they can start to see what things might look like fitting all together. You guys are about to do the same kind of thing for the assemblies for the four-wheel drive cars. So one of the things you guys have as homework is to send me a message with your proposed team of approximately 4. So some teams will be like 3, some teams will be 4 for the four-wheel drive car. It's helpful if you use your table groups as a reference. So make sure you guys get those to me. All right. So this is a really neat, really clear layout. There's a lot of things that you can figure out in terms of packaging. You can do thermal simulations on some of this. There's a lot that you can do once these are finished assemblies. You can also find a component. But you have to be under the Circuitworks tab in the ribbon here. So it should be able to figure itself out. There's still varied usage going on. There we go. Why it takes quite this long, nobody really knows. So you select the component that you're interested in, and it should show up. Then you can change properties. You can rename it. So as with the other tutorials, this particular assignment shouldn't be all that scary. So then you can do annotation. There's supposed to be a link right here with annotation. You're not supposed to have to go to the tools menu for every little thing. Except in this case, we have to find where it's hidden. Let's see. Yeah, that is the resolution as far as like display scaling and everything should be under display. This component individually isn't any different resolution. This is just a representation. However, like I said, you're going to want to not be in 4K, 1440, and whatever else retina ratios. That's very bizarre. Why? In assemblies, you can annotate things, and it's a cool thing that you do. There we go. They exist, but that is not very helpful. Yeah, each of these should this was present earlier, and it is not there now. Very interesting. By interesting, I mean exceedingly annoying. Yeah, the size is fine. What gives? No, we don't want dynamic annotations. Very interesting. So it's supposed to be a couple other places. Huh. I thought yesterday I was able to find it in one of the tool menus, but it is not there. So it's only going to be under your Circuitworks ribbon in the command manager that this annotate component shows up. This is part of the reason I'm going through some of this stuff with you guys, because there's a couple things that are supposed to work a little bit more easily on it. All right. So you're looking for, in this case, top level components, and this is going to be saved as, and then my cell phone. So the reference designator or component name, both are acceptable. Sometimes you'll want the component number only. Now it'll also be possible to sort of identify what's what. The names are going to be a lot longer than the component designations. This one, I think, is memory heavy for whatever reason. Yeah. It takes a while to finish naming all of the actual components. It's doing a fair bit of processing. The other point of walking through some of this with you is making sure you don't expect. There we go. Sheesh. Making sure you don't expect this to go quickly. There's now 88 annotations. You should be able to show and hide them. We're having strange SolidWorks behaviors today, which doesn't help. All right, so the annotations are there. We're going to save it before things go catastrophically awry. And then we're going to go through an export. So once we've done this process, come on, here we go. Once we've done this process, so that's our let's see. Yeah, let's take a look at the board itself. No, this is not. This is just not showing up correctly here. So I think I'm getting a combination of Zoom helping and a couple other things all at the same time. So anyway, we're going to go through an export process. So export to Circuitworks. This one shouldn't be nearly as resource intensive. However, still takes some time. There's enough going on in the background that this has been the only way I can tell whether processes are still proceeding or not. There we go. So remember when I said it takes a few minutes? Yeah, wasn't kidding. I've got a handful of cores to throw at things. So you'll want to give yourself some time on this assignment. Make sure to not be trying to start it at 10 p.m. or 11 p.m. on Sunday night. It's a bad plan. It was always a bad plan, but it's even worse of a plan when you forget the assignment and then it takes 25, 30 minutes to render that part on your machine. Not much I can do about it. So more resources don't necessarily help. It's just a matter of time. All right. So what we can do is with the two together, the compare will actually highlight what some of the differences are. And it's supposed to highlight them clearly and give you a summary. So you can see some of the detail down here. Yeah, you can see some of the detail down here. So the main difference that it finds between the two is the addition of the H199. So aside from that, there's no other major version changes. So this is important when you're doing iterative designs and all of those sorts of things. And you can follow this same IDF 3.0 standard as far as file information and what's being stored. So then we're paused on this for a little bit. I'm sure you guys will end up running into a couple minor things related to this. I found the library to be a lot smaller than I would have guessed. But so long as you've got the majority of these things up and working, it shouldn't be a huge issue. This board is a good example of how we put together an assembly from a lot of much smaller components. Some of them are pretty tiny. In this case, I think you're just getting surface features, but you've got a large number of resistors. So there's a lot that goes into this model, and that's why it takes a minute or two for all these operations. So lots of things going on there. All right. This at least gives you a starting point for how some of this works as far as the assembly. The question is, how do we apply that to this four-wheel drive car project, and what are we doing with it? So I'm going to not save all so that the next classes can take the same punishment you guys had to. We have a couple components, one of which is, let me switch over to this mode here. So these boards, what they're going to do is control the motors for the four-wheel drive cars. What you guys haven't seen are chassis that you're going to have to design yourself. You'll be given batteries, gears, some number of shafts, motor, a couple pigtails that go to your control board. And at the end of the day, it has to be a functional four-wheel drive, because that's part of what you're graded on. In this case, I didn't like the default wheels and tires, so I printed both the wheels and the tires. There's not really a benefit to that exactly, but ultimately what you're going to be doing is designing a body. Obviously, I designed that completely from scratch, just in my spare time, and design the wheels to go with the overall package. So what these do is they run at ideally a consistent RPM when switched on. All four wheels are running, and it goes around the track, and then you set a world record. Or you don't quite get around the track and you don't quite get full points, and it's all down to things like what your actual gearing is. This one has a couple of components that you won't be able to get your hands on because this was trying to get set up as a top speed run car, and these motors are down in the range of, at least some of them, milli and even micro Newton meters of torque, which means if an ant were to be resting on, one hand on his hip and the other hand on the wheel, they wouldn't be able to turn. So that's not a lot of torque. That's literally the kind of torque that ants could produce. So not very robust overall, but the board is what we're focused on. And that's where you need some of the schematics that we've got. So a few of those include the LED, the resistor, but the most important component to start building out for that assignment is this one. So what this does is gives us the spacing for components, and this has been revised since earlier in the week. as we didn't have all of the Eagle files and everything else, I had to recreate all of this from the remaining prototype that I've got. So there are a few components that go here. One is the 3-pin connector, which we use as the motor connection. So even though we only have 2 active pins, the 2-pin connector next to it is where the LED goes. The resistor goes across here. You have the 2-pin power connector down here. So this goes over to your battery box. And these two ideally are mounting holes. This last one being the switch to engage power. So this doesn't include the actual copper layout for the boards. I don't know if we're going to have enough boards. I'm working with the lab staff to make sure that you guys have supplies. There was a lot of damage and carnage apparently last semester. So I'm not sure how many of those components survived. We may be pretty short on components and have to print a lot of extra stuff this time around. We'll find out. So in the meantime, we're going to recreate them. This you're going to need to do in a couple different steps. And what I'm going to set you guys up for is to start working a little bit on a couple of these. So you need to create your LED. So a couple of these components have spec sheets. So this is a whole lot nicer than trying to guess. So you want to make use of these as best you're able. These give a lot of really important detail, especially things about spacing. The spacing of these don't have to line up exactly with the holes in a real circuit. You're bending stuff around anyway to fit and accommodate where it needs to go. One of the ones that's going to be harder is toggle switch. So this is about the same part number, more or less, as what is installed on most of the boards. These are a special category of toggle switches. These are sometimes called micro minis. So real small jobs, able to handle a surprising amount of current. So sometimes they're able to handle upwards of a couple amps down below 200 volts. So this one is a 3-position example. Ours is a 2-position example. So it's a single throw, single pull. So that's what this guy is trying to represent. But there are a few different positions for this one. The physical dimensions are the same. So all we have to do is create one of those. But this is one of the other things that you have to create in order to replicate that board. In order to bring it into SolidWorks, one of the other things that we need to pay attention to is I don't know if I can get it to recreate the board cleanly or not. I was trying to since I didn't save those, I will have to recreate it real quick. Actually, I don't want to do it because I can open it from here so long as, come on. There's two kinds of extrusion cuts in this model. That's what I'm trying to get at. I'm trying to see if it will allow me to actually open the board file, or if that's one of the issues that's causing problems. So there's two types, plated and non-plated. But the board itself is supposed to be listed in the components, and it is not listed today where it should be. So Circuitworks is doing something interesting. I just don't know why there. Let me see if I can fake it out this way. Should be able to, yes, overwrite the board. All right, so I can get there this way. Fine. Come on. Brute force is acceptable certain occasions. All right. Just don't hurt anyone that doesn't deserve it. Bonus points if you know where that quote's from. Okay. So this feature is just an offset depth to extrude up to this dielectric layer. It's not anything special from Circuitworks. The outline is a really rudimentary sketch. Anyone know how they came up with this sketch? There's no dimensions on it.
Is it based off of Nokia?
Yeah, what they did effectively was they traced a they traced the picture for this, and what they did is fit piecewise components to this. So they did arcs and arc segments, spline segments, and whatever else. I don't see the handles for a lot of spline segments, but that's what each of these, I guess technically some of them are arcs with really long radii. But that's how they created this original component. So the whole point of this is that it's not something special or unusual. They did a few different cutouts, so nothing unusual, but they separated out these separately. So The drawing itself doesn't have any magical, mystical properties, but they did group two different types of extrude cuts for holes. The NPTH, which is non-plated through hole, and then PTH is a plated through hole. So they grouped them into two different categories from two different sketches. There's probably a good reason to do this if you're doing Circuitworks, so that you can categorize the two differently. And I don't know if it's tied to the name or anything of that nature yet. I have to do a little bit more digging. They also did an extrusion here. That's the keep out. So maybe they need room for the mechanism that hits the button or whatever it is. It's about the kind of space you might need for that, based on using this as a mounting hinge or something. So anyway, that's how this particular part comes to be. Once that part gets pulled into Circuitworks, the plated through hole group and the non-plated through hole group are treated differently inside of Circuitworks. And that's kind of the whole point of this. So we need to know information about those. I don't know if those get selected or if those can just be matched to different features of the drawings. I haven't gotten a chance to get that far yet, but that's something I'm going to experiment with here as you guys get a start with drawing this. So I'm going to say no, I don't need those changes. So you guys start with the boards and see if you can create them. It's a whole lot faster since you have the part drawings now. It'll be a whole lot easier. And then start creating some of the LEDs and all of the other things so that you can put together all of these components as an assembly, because ultimately we have to put these together as an assembly. Probably later in the week, I'm going to give a little bit more guidance, but I want to try and take a couple of the parts and then see if I can pull them into Circuitworks and close the loop on that whole process. So I'm going to give you guys a little while here to start working on a couple of these components from the drawings, and then we'll come take a look. So I might demonstrate a little bit about the switch, since that one's maybe a little bit more complicated than some of the others. The 2-pin header and 3-pin header really aren't all that complicated. Those will be pretty quick parts to put together, so that shouldn't be anything unusual or super difficult. All of the details should be there in the drawing. So all the key dimensions, depths, and so on. So that shouldn't be a big issue. Toggle switch is probably the hardest part out of everything. So then we can put together an assembly with the board. And that's part of what you guys are going to be working on in order to start modeling the entire vehicle for your CLC project. So this is why it's also important to get me the requests for the groups in the messages forum, because that will at least give me a chance of getting this up and running so you guys can start creating some of the parts, because we're going to need to start creating parts and getting them printed off from the 3D printers. I'll have to find out if we're going to be short on gears and some other things, because we may have to get some components ordered here very quickly. So I'm also working with the lab staff to try and answer some of those questions. All right. As you guys start on this, any initial questions? So once we've got this component setup, the reason I recommend doing the naming similarly is it looks like Circuitworks can pick up on the nomenclature. So if you do two separate features, even if it's from the same base sketch as it is here, doesn't have to be a separate sketch. Even if it is, it looks like Circuitworks is picking up on it. So when we go to export this as a board instead of an electrical component or mechanical, we have to select the top face. So we need to select just the top face of the board. In this case, you want the 2 pins. So actually this one, the way this is set up is opposite to where this would be the top face. So the way that my board is soldered specifically, the resistor goes here at the bottom. The LED goes here, motor power connector here, the power connector from the battery here, and the switch goes here. So this would be the top face. So then we'll let it use the silhouette edges. That should be sufficient for the board boundaries. So it's recognizing for the non-plated through hole. And for the plated through hole, our features. So this one, there are no keep out areas for this one. So if we did have another extrusion that we needed to select, that could be represented as our keep out feature. So if we wanted to leave a space for the switch, which is rather large or whatever, that's where we would do that. So we might have to put it together as an individual assembly. That's what it looks like. Yeah, it looks like it's going to need individual assembly. Okay, so that gets us several steps closer to how to bring it back into Circuitworks. Because I don't think you can do any component assembly from this window, which is the next step. Yeah, looks like it has to be, no. Looks like it has to be put together like a regular assembly first, which does make some sense. So if we start with what we've got, control board, there's going to be a few more. and header LED. All right, that'll give me a start. All right. So we'll do a couple things you guys should be familiar with by now. Round pins are going to make this interesting. So we parallelize a surface and another surface. Nope, want them co-parallel. Good. Actually, I want to reverse this, fix this, float this. This one should be fixed. That one's floated. Good. It's reasonably close. Now, this we should be doing similar thing here. This parallel to this face. And making, we'll say this face parallel. Keep our orientations. Get sort of close. Okay, now concentric. Don't remember if we can use, I don't think we can, because best we're going to be able to do is tangent. For this purpose, that'll be close enough. Tangency, let's say okay. So it's storing that tangency. Tangency is not helping. So I'm going to go change those.
Yeah.
There should be a better option for that. Maybe I'll stick with coincident and see if that cooperates better. So base the weakness to coincident and why I prefer others is, oh, I bet a profile standard would do it. Yeah, profile center. Perfect. There you go. Profile center. Learned something new today. Hadn't had to use that one before. Makes sense. Profile center. Now, the only thing I don't know is if it needs to be fixed. Maybe it does, maybe it doesn't. So I probably need to change the height of this. Sometimes manual adjustment is required. I'm going to say 2.3 is right about ideal for that one. Same deal here, 2.3. Call it good for the profile centers. All right, those two are set. This guy, this face. Check. This surface. This surface. Check. Good enough. This one probably also profile center. Nope. Circle. Rectangle. Okay. Get it moved closer. I want it. Coincident is the problem. As always, I'm going to be real careful. Profile center. Try that again. Control Z is your enemy. Just that. 2 millimeter offset. It's usually about right. Okay. There we go. We have a couple components on our board. This is enough to do a test because we're coming up on time. By now, you guys have long since been turned into oatmeal. Leave those mates in place. Now, export. See if this works. First, I'm going to save this. So this is a quick update based on some of the other things I've been able to complete for this particular project. What we're trying to do is put together this entire assembly. Each of these is a custom component. So the way that these are going to behave is going to be different based on what they're trying to do. I've changed some of the alignment of things to be as centered as reasonably possible. Change the pin alignment. I've gotten all but the switch to show up sort of correctly. There are a few aspects that are not allowing me to customize them, so it still has a few of these holes showing up as both plated and non-plated. Not a whole lot that I can do about it, but by deleting some of the things I added into the component group, there is a section under Program Data and SolidWorks, Circuitworks. You can add boards and components for whatever reason. By adding those into here, it made it difficult to get any of these things to show up. So I don't know why exactly, but that's something that I'm going to have to work on a little bit further. The main thing right now that's important is each of these components is physically represented. So the switch is there, it's just not showing up as being complete. And so this one, there's still some kind of an error. I've tried doing model association and a couple other things. So I may play around with this some more, and if I come up with a fix, I'll let everybody know. But what this will do is at least allow you to see how these things are done. So the objective is to build the complete assembly, then export to Circuitworks, show that you have the diagram, and then take it back over to, and in this case, we could add in the traces and other things. Right now, that's a bit too much in total, so it's not really something that we want to do. For the purposes of this project, we just want to make sure that we can export it, and then we want to bring it back as a built model and verify that what we think this is actually looks like it does. So if we save this and close it, then we jump back over, have it build out the model. I'm curious to see what it comes up with. Okay, so it sort of, kind of got things partially correct. This component is it thinks showing up significantly off the board. So I may play around with the spacing and see if that distance helps fix some of the issues. Some of the other ones have mates that associate them a little more closely. This one doesn't necessarily have that last piece, and that may be why it's not showing up the same on the board, but it at least is producing something loosely resembling what we started with, which is good. So we're going in the right direction there. For the purposes of grading, I'm not going to be busting you guys' chops over this incomplete process. The idea is to demonstrate a closed loop, be able to build the concept, export it to Circuitworks, bring it back in as a completed model, and all the components behave correctly. That's the big idea here. So that way you can model things. So obviously this needs a little bit of tweaking with some of the definitions, but working broadly in the correct sense now. So hopefully this will help put you guys on the right track with regard to building out these circuits and using this module. Some of the Circuitworks stuff is a little bit clunky. I've had to close and reopen SolidWorks a few times to dissociate versions of this that I've worked on. So maybe that's some of what's going on, but overall it can work if you are patient enough with it. So I'm going to see if I can fix that last feature, and this should hopefully put you guys in a good position to be able to get the detail and the data and the completed project as you're working on this.